Well, this is session 5 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton Fick. In the first 4 sessions, we've been mining issues where we have dichotomous exposure, dichotomous case control status or disease status, and dichotomous potential confounder modifiers. What we're going to do in today's session is look at the first significant departure from stratified analysis, in that we're going to be dealing with variables that are not dichotomous or not discrete, and where we've made the decision to express the relationship between the outcome and the explanatory variables with, well, for starts, one line. And then we'll expand it to several lines. So we will not, with this material, have the ability to trace things back to the stratified analysis. However, I think we've solidly established the beginnings to, I hope, the beginnings to understanding of logistic regression, so that it won't be that intimidating now to think about the implications when we have lines. Okay, let's see. For an illustration, let's suppose that we have a study in which a person's actual age was measured. And maybe it was measured actually in days, or perhaps years. We'll look at the unit of measurement as being an important issue as we look at variables which are measured. So it's true that we could, in principle, say, well, let's dichotomize these ages into 2 groups, the young and the old. There are many reasons why authors don't want to do that. And in part, it can be that if the relationship happens to be a comparatively simple one, involving actual age, then we may get far more in our understanding of the issues involved than if we had used, say, just young and old age groups. So for our consideration here, we'll suppose that age is considered to be a potential confounder or modifier, and that previous research is considered actual age rather than age groups. And the largest issue is, did you actually measure the age, and did you do so by appropriate methods that give you, say, something that we might even view as continuous, an age that is, for which there's just so many possible values, especially if, say, we're able to measure a person's age in days. There's no way it would make any sense to try to have an analysis based on all of the different ages. Okay, so let's suppose then that we have a model that you're going to say, for the start, looks quite familiar. We've got the log of the odds of exposure, and then we've got disease status, and age, and then D times A again. But the difference here now is that A is now, for this illustration, is age in a person's years. So perhaps the days have been converted into years. And we'll talk about, again, as I mentioned, we'll talk about the units a little bit later on in this session. Okay, so we're now going to be thinking about the log of the odds of exposure as a function of age. Okay, and you can see it's actually going to be a straight line, or a line, right? Okay, now since we're going to be studying the relationship between the log of odds and a measured explanatory variable, well, what are we going to be dealing with? Well, here then is a graph where I've got log odds on the vertical scale and probability on the horizontal scale, but logarithmically so we can see things. It looks like for most investigations for which the probability of exposure is small, we're going to be dealing with negative numbers for the log of odds in the range between -2 and -10. Something to keep in mind when we're trying to understand and interpret the results that we're going to be seeing. So log odds are, of course, any number, positive or negative, but for most of our work, it's going to be something where we're going to be dealing with small numbers. And here's the relationship between, say, -2 and -8 approximately. Okay. So let's now explore or try to understand this model where A is the person's age, the participant's age in years. Well, let's now think about how age from this model can be seen as a modifier, or at least a possible modifier. All I've done is taken this equation and grouped the second and the fourth terms that both involve the disease status indicator. So then we can see very directly, because we've been looking at this for a while, that this thing is capturing the log of the odds ratio. We've done this before. And so we can see quite directly that this equation is giving us an equation for the log of the odds ratio that is a line. Okay? The log of the odds ratio is a line, and that directly comes from this. But so we can see then that if the log of the odds ratio is a function of A, then that says that age modifies. Right? So beta 3 then, you can see, if it's not 0, that's saying the log of the odds ratio depends on age. And that's the same thing as saying that age modifies. Now, though, we can see that beta 3 is not the same form that we saw before. What we saw before was that beta 3 could be seen as a difference. Now what we're going to have is that beta 3 is the rate of change of the log of the odds ratio per year of age. Rate of change. And then you're thinking, oh, I think I remember this from my math courses. Beta 3 is a slope. Right. The odds ratio continues to be the odds of exposure among those with disease divided by the odds of exposure for those without disease. And then we can see quite directly then, if the odds ratio depends on age, then age is a modifier. And that we have seen then, if beta 3 is not 0, then age is a modifier. And what you can then realize is that although we've changed from age group, just 2 age groups, to an actual measurement of age, the interpretation of age as a modifier when beta 3 is not 0 is the same. However, the way in which it modifies is different, right? It is this slope now. Another way to see this, well, if we were to think about the fact that there are, in fact, with this equation now, two lines. One for the folks that are controls, and one for the folks that are cases. And what do we see straight away? So beta 2 is now interpretable. It too is a slope. It is, in fact, the rate of change of the log of the odds of exposure per year of age for those who are controls. Then we can see again that beta 2 plus beta 3 is now, again, it's a slope. It is the rate of change of the log of the odds of exposure per year of age for the cases. Okay. And we can see quite directly that this model then gives us two lines with possibly different slopes. When are the slopes different? When beta 3 is not 0. Two lines. And the two lines are parallel if beta 3 is 0. We're gaining experience now and are able now to translate the model interpretations in terms of epidemiological language, and they're almost the same, but differences have now become slopes. Well, what if we were to explore this equation, for example? Okay. What's happening now? There's no beta 3. That's saying that this now gives us two lines that are parallel. And then we can see that beta 1 is in fact the vertical distance between the two parallel lines. And it's the common vertical distance between those two parallel lines. It is the assumed common log odds ratio. Wow. Again, this is similar to what we've done before, but instead of it being a dichotomous potential confounder modifier, it is something that's captured with a line. So this is just like what we saw before. And now that fixed vertical distance between the two parallel lines captures the assumed common issue. A bit about the units now. As I mentioned, perhaps we actually had the ability to measure a person's age in years. Maybe their birthday was noted, and also the day in which the study was conducted, and then a method to convert from their date at which the study was conducted and their birth date gives us days of age, right? So we could convert to days, if we wish, with this admittedly somewhat approximate method, this 365 and a quarter. It can be done with a more detailed thing, but the whole idea here is that it's a scale change, really, pretty much. Duration data is typically measured in seconds or minutes, hours, days, weeks, months, years, and in all of these occasions, the changes are merely changes in scale. There is 60 seconds in a minute, and 60 minutes in an hour, and so on. Now, temperature is a bit different. Temperature is something where we have Fahrenheit, perhaps, or Celsius. And now the change is a location scale change, okay? And there's the simple expression for changing from Celsius to Fahrenheit or vice versa. Another one that's commonly seen is concentration. And here the transformation, if I like, is sometimes to the logarithm. Acidity might be pH, which is the logarithm of the concentration. It's worth noting here that these that the changes we're making, these transformations we're making, have an effect on the models, but in fact, when the transformation is linear, and the location scales examples, those first two we had, age and duration, we see that the regression coefficients change, but we will see that the fitted values don't. The fitted values do not change, and we'll explore this in a bit more detail later. On the other hand, the switch between concentration and the logarithm of concentration is what's called a nonlinear transformation. And not only do the regression coefficients change, but the fitted values will also change. Another issue when we have a measured explanatory variable is the possibility of centering. And this turns out to be a valuable thing to consider so that regression coefficients that we're wishing to study have interpretation that makes sense to us. It turns out that if we replace x by x plus c, that is just a location change, and so the fitted values won't change with simply a centering process. What are the implications? Well, it means that the regression coefficients in some settings will then become specific to that centered value, to x equals c, rather than to x equals 0. And again, this turns out to be important for interpretation at times. For example, it may be that we're not dealing with the very, very young, or in fact, when children are just born. So age equals 0 is not possible. But we might have 20-year-olds in our study, and the range of ages might be somewhat around that might be, say, the center of the ages, roughly. And so the switch from A to A minus 20, so again, the actual explanatory variables now don't have as simple or as familiar an identification, but the regression coefficients do. Yes. One other point that's worth making here is that indicator variables, the 0-1 dichotomous variables, we don't center. There's no meaning to centering an indicator variable. Here's a small example. Let's just suppose we have an equation that looks like this. So you can see that I've centered age at age 45, and I'm considering a slope that does depend on disease status. And then we have this number as well that depends on disease status. So what are we getting in this instance? Well, for the controls, we get this line, and for the cases, we get this line. Notice that for the cases, the slope is steeper. It is higher. All right, the line has a steeper slope to it. Okay? Now let's look at a visual to help us to understand things here. But before we look at the visual, let's just notice that this equation can be specialized to individuals who are age 45. And then we can see that for those folks who are age 45, then minus 2 is their log of odds of exposure. Same thing here. If these folks, if we think of a person who's age 45, then this number here becomes the log of odds of exposure for the folks who are age 45. And here is all of that in a couple of graphs, a couple of lines. There's the control line, there's the case line. Here is where we centered the age 45 folks. And there is the values, sometimes called the intercepts, at age 45. Okay. We can note that if this were the result of an analysis, say these were the actual fitted values in an actual study, we would see we have an indication that age modifies because the two slopes are different. All right, let's look at an apparently simpler situation. In this one, we're going to have a constant slope that does not depend on disease status. So both of these lines have the same slope, but differing values depending on disease status. Okay. What are we getting in that case? We get, for the age 45 folks, we get minus 2, and for the age 45 folks, we get minus 1.6. And now we get two lines. We get two lines with the same slope. And the vertical distance between these two lines is capturing the assumed common log odds ratio. So this difference here is, in fact, the log odds ratio. You can see that here. The difference between this line, this horizontal line, at minus 1.6, and this horizontal line at minus 2, those are two log odds. The difference between the two log odds is the log odds ratio. And you can notice not only is that distance of 0.4 or minus 0.4, depending on how you display it. This distance here, but it's also the distance for the 60-year-olds, not just the 45-year-olds. This vertical distance is the same for the 60-year-olds as it is for the 30-year-olds, right? The equation is displayed in terms of the 45-year-olds, but the differences, that's the crucial thing, isn't it? The difference is what is capturing the log odds ratio in this instance. Now, one more brief point, and that is maybe we might have a measured exposure. Okay? Maybe it is the length of exposure, the duration of exposure, right? Or it could be a dosage of a drug. And for purposes of understanding the relationship between, say, an outcome and the dosage of the drug, we might suppose that a line will do the job for us. Right? So we might then think of exposure as the measured characteristic and the potential confounder modifier as a dichotomous variable. So this is the same circumstance for us here. It's just we've interchanged the characteristic that's measured with the characteristic that's dichotomous. Now we can see that in order to study, in this case, the probability of disease or the log of the odds of disease, we're going to be dealing now with 3 equations, possibly. And the associations between disease and exposure are now measured as slopes. Okay. Possibly beta 1 plus beta 3 now being a slope that's capturing the association between disease and exposure. And so we've got exactly the same circumstance here as before, except we've interchanged the dichotomous variable with the measured variable. And I hope that's clear. We can see that, for example, in this instance, we get 2 lines for exposure. We get 1 line for the men and 1 line for the women. And the lines have different slopes if beta 3 is not 0. Further, we can see here that with this equation, the 2 genders have the same slope. The relationship between the log of the odds of disease and exposure is the same for the men and the women. And so we can see that this last line would be analogous to a crude analysis, right? Where there is no consideration of gender. So this particular equation enables us to assess gender as a modifier. And then these 2 equations enable us to assess gender as a confounder if we have ruled out that gender is not a modifier. All right, time for an example. And this particular example is taken from a study of child health. And we're dealing with birth weight of a newborn, the gestational age of the pregnancy, the smoking status of the mother. Okay. And we're wondering about the relationship between the birth weight and smoking status and gestational age. So for this illustration, what we'll do is suppose that we'll be looking for birth weights that are low. For this illustration only, let's use the dichotomization of birth weight as being low birth weight if it's under 3,000 grams. Now, you might say, well, that number 3,000 is too high, and that is a good point. It's been observed that for this illustration, that maybe we might want to try different values for this threshold, if you may. And rather than keeping the actual amount of smoking that the mother did, we'll simply note, did the mother smoke during pregnancy or not? Yes, no. And then we'll have the gestational age. Okay? And that is measured here, the actual gestational age in weeks. So what is the circumstance that we're dealing with here? All right. We're going to think of the outcome as low birth weight, the indicator for low birth weight, and the, if I may, the exposure here is mother's exposure to cigarette smoke. But it's noted here that we must consider an analysis that includes gestational age. And so we'll be wondering about gestational age as a potential confounder or modifier. Or perhaps it will simply be a characteristic that is associated with low birth weight. And we'll come back to this. There are several issues. Okay. So as we did in the previous examples that we've seen previously, let's try a logistic regression. Let's model the log of the odds of a low birth weight infant in terms of maternal smoking, gestational age, and then the smoke times gestational age characteristic, the product of maternal smoking indicator with the gestational age variable. So now we're going to explore this logistic regression, and you can see that we're going to be getting two lines. Let's study this now. What do we get? We get that, and we might begin with the study of the estimate of beta 3. We can see it's a tiny number. And it is not statistically significant. So that suggests then that gestational age does not modify the relationship between low birth weight and maternal smoking. Then we can explore two lines from this model. And here is how one way we can do this with Stata. First, we save the fitted values in a characteristic, in a variable. We'll just call it YH for Y hat. Well, maybe not the ideal symbolism, but it'll be due. This option XB, we'll just leave it aside for now, and it will be explained in more detail. There are a variety of different options you can use with predict, and this is the one we need here. So this is giving us the fitted values in this instance. Then we can use in Stata a two-way command that plots the line for the mothers that did not smoke and the line for the mothers who did. Okay, let's have a look at these two lines. It turns out that the blue line is for the mothers that did not smoke, and the red line is for the mothers who did. So we can see the red line in this instance looks to be the red line and the blue line look to be nearly parallel. That's supported from the fact that this difference between the two slopes is tiny here. Aha. And we can see the red line and the blue line both have negative slopes. Does that make sense? Let's think about that. Remember, the vertical scale here is the log of the odds of a low birth weight infant. Now let's just explore that a little. The higher the gestational age, the lower the log of the odds of a low birth weight infant. Aha, that makes sense, doesn't it? Okay. And we might be thinking, oh, I'd like to have the means of assessing this vertical distance and determine whether or not that's important. In other words, is in fact maternal smoking associated with low birth weight infants? So in this instance, since there's no evidence that gestational age modifies, it suggests refitting the analysis, refitting the model without the M or the smoking, the SG term. Okay. And if you do so, then you get something that's quite important. We now get assumed common applying here. Let's see if we cannot make sense of this. What do we mean by assumed common? Okay. This slope estimate, this estimate of the rate of change of the log of the odds of low birth weight per week of gestational age, is common to both the maternal non-smokers and the maternal smokers. And we can also see this number here, which is the estimate of the vertical distance between the two, between the maternal, it's the assumed common vertical distance between the two lines. I've not done that terribly well. So this number that's nearly 1 is capturing the vertical distance between the two lines, assumed common to gestational age. In other words, it applies to any gestational age. Let's go back to the picture. I haven't redrawn the picture because they're almost identical here because of the fact that up here there was almost no difference. But if you look for say a gestational age of 35 weeks, this distance, this vertical distance, is about 1. Right? And it's about 1 for 40 weeks as well. Okay? It's about 1 for 42 weeks. The difference is assumed common to gestational age, and the slopes are assumed common to the two smoking groups, maternal smoking groups. Okay. Now you could ask, should we have bothered to include gestational age? In other words, is gestational age a confounder? Has the message changed meaningfully in going from an analysis that adjusts for gestational age to an analysis that does not? I've done the analysis that does not in 2 ways: the usual stratified analysis, the simple 2x2 table in this instance, and then this number, which turns out to be the logarithm of this number. Okay, the log of the odds ratio estimate is 1.012, approximately. Okay. So what do we see? If we had adjusted for gestational age, then the assumed common difference between the smokers and the non-smoking mothers is about 0.945. But for the crude analysis that does not adjust for gestational age, we get a number that's only slightly higher. Okay. So that in that instance we would say, you know what? it doesn't appear that gestational age confounds. However, in this particular analysis, because in the field of the study of low birth weight, all analyses ought to involve the inclusion of gestational age. Reporting an analysis of say, risk factors for low birth weight infants has to include gestational age. So even though gestational age does neither confounds or modifies, it is still felt to be reportable in the analysis, and I hope that's clear. This has not come up for us before, but this is a very common circumstance. Still, the identification that gestational age neither modified or confounded is interesting to report. But in this instance, the analysis that would be reported is the one that's adjusted for gestational age. And now here are the two sets of lines. The red and the blue line are the fitted values drawn for the line with adjustment for the two lines with adjustment for gestational age. And then the yellow and the green lines are the two lines where there is no adjustment for gestational age. And you can notice, I think, fairly clearly here that when we do not have gestational age in the equation, then the relationship between the log of the odds of low birth weight and gestational age has slope 0. That makes sense. They're horizontal lines. Just included here for clarity, I guess, or some identification. And we can notice that the vertical distance between the yellow and the green is almost exactly the same as the vertical distance between the red and the blue. And that's, again, a pretty clear and pretty helpful set of circumstances. Now, I've intentionally here not included a legend that details what each of those lines is about. We've got the two lines from the first model that explored gestational age as a potential modifier, and then these two sets of lines exploring the issue of confounding. And it is a good idea to help, and it can be very helpful to your understanding to spend a bit of time determining which lines are which. And then you can, of course, there's ways with Stata or whatever software you're using for displaying a nice legend that would identify that for you. But when you're learning, it's helpful to, work through it. Okay. So up until now, we've been modeling the log of the odds of a low birth weight infant in terms of maternal smoking and gestational age. But you might have been thinking, wait a minute, this particular study can be viewed as a case control study, and it might well be that it's more reasonable to do so. In other words, we have the children and their low birth weight status identified at say the present time, the gestational age also measured in the present time, and then we looked back in time and explored whether or not mother was smoking during the pregnancy. Right. So, in fact, the first model that we've looked at here might well be one that maybe isn't the most most directly associated with the issues here. Now, this is somewhat borderline. Nevertheless, I think it is of considerable value now to re-explore, to reassess this study and the limited goals that we've established here, and that being, is there a relationship between the log of the odds of maternal smoking and lower birth weight infants? Or is there an association between maternal smoking and low birth weight? Okay. Now, if we repeat our analysis now, let's do so. So now we need the product of low birth weight and gestational age. And the logistic regression then would be the log of the odds of maternal smoking as a function of those three explanatory variables: the indicator for low birth weight, gestational age, and then the product of low birth weight with gestational age. And if we did that, well, we get what definitely looks like a quite different story in some respects. Let's take them in steps, though. Notice the logistic regression equation gives us fitted values that do not directly compare with the coefficients we got from the first model, where we were modeling the log of the odds of low birth weight. Well, all of those characteristics have different interpretations now, because they're all being interpreted in terms of the log of the odds of maternal smoking, not the log of the odds of low birth weight. Further, the visuals we get are very different. One thing we might notice is that for the for the non-low birth weight infants, the slope or the relationship with gestational age is as shown. It's negative. Right? That is the relationship between the log of the odds of maternal smoking and gestational age. But when we look at that particular equation now for the low birth weight infants, what do we see? We see that is the sum of these two numbers, and we get a sum that is nearly zero, or is very close to zero. So what is this fit going to look like? We're going to have a line with negative slope for the children that are not low birth weight, and a slope that's nearly zero for the children that are low birth weight. Let's have a look now at that visual. Here are the two sets of lines in this instance. The picture is so different from what we saw before. Here are the non-low birth weight infants, and here are the low birth weight infants. This is the log of the odds of maternal smoking. Okay? Remember, we're viewing this now as a case control study. Notice that since we're using the fitted values, we've computed the fitted values using stata's predict command. And notice that the red line, of course, has this nearly zero slope, and the blue line has this negative slope. But notice that there's this group of individuals in this that are low birth weight and low gestational age. Right? Further, these high gestational age children there are none with low birth weight. Right? See that there? Now, we can go back again and see that these two lines have different slopes, one near zero and one negative. However, the difference between the two slopes is not statistically significant. Further, we can also see from this analysis is though although we have shown a negative slope estimate for the log of the odds of maternal smoking and gestational age for the non-low birth weight infants, that is not statistically significant. Okay? And the same thing is true for the low birth weight. So what we're getting is a very different story now when we're modeling the log of the odds of maternal smoking. The message is different. Notice this picture very different from the picture that we saw in the first set of models where we were modeling the log of the odds of low birth weight. This is a point I made in session 3 about the fact that the fitted values from the two models here, right, the so-called inverse model and the sampling model, the fitted values are different. The circumstances are different. Okay. Now what? Well, since we have no evidence of gestational age as a modifier, we can repeat this analysis without the product of low birth weight and gestational age. Now something interesting happens. Okay? Still not seeing an association between the log of the odds of maternal smoking and gestational age. Right? That being assumed common to both the low birth weight and non-low birth weight children. And the also assumed common characteristic we have here, this 0.95, that is the vertical distance between the two lines, okay, assumed common to gestational age. So that's the vertical distance between the low birth weight and the non-low birth weight infants, adjusted for gestational age, or assumed common. And further, we can also see that if we then consider whether or not gestational age is a confounder, we repeat the analysis without gestational age, and then we get a crude estimate. We get a crude estimate of the log of the odds ratio in this analysis, and here is the adjusted estimate of the log of the odds ratio, the 0.95 and the 1.100. Okay. So let's look at a visual for this. Here are the two visuals. Again, we're seeing two lines with adjustment for gestational age and two lines without adjustment for gestational age. And as I noted again, the vertical distance between the red and the blue line is about the same as the vertical distance between the yellow and the green line. That suggests that gestational age is not confounding. Okay, notice again from this display that we're seeing that the low birth weight children are represented amongst the very lowest of gestational ages. Similarly here. We're getting different information, aren't we? Okay, let's go back now to all of this. You might be thinking, wait a minute, I've analyzed this now as a case control study and using the sampling model as named and as described in the book by Keogh and Cox. And what do we get? No evidence that gestational age modifies, no evidence that gestational age confounds. Okay. Still with this study, it would be argued that gestational age should be included in any analysis here. And sure enough, if we do so, this would be the reportable characteristic, usually. Right. Now, so nothing in here is essentially the same as what we saw in the parallel lines with modeling the log of the odds of low birth weight. The lines are different. They're measuring different things. And where are things the same? Only in the crude here. And only in part of this analysis. Let's look. This number, 1.01179, is the estimate of the log odds ratio. But we can now recall that that log odds ratio is the same whether or not it's in terms of the log of the odds of disease for those exposed divided by the log of odds of disease for those unexposed, or the log of the odds for exposure for those with disease divided by the log of the odds, or subtracting the log of the odds of exposure for those who do not have disease. Okay? So this number, 1.011791, is the same as the earlier one. Let's look. There it is. But notice the constant terms are different. And I'm going to leave that aside for the time being. Leave that out for our discussion. Okay? They are not the same. Now, so what it is important to realize here is that identifying how you wish to analyze data. Do you wish to analyze the data from this study where the outcome is viewed as the log of the odds of low birth weight, or do you wish to analyze it as the outcome being the log of the odds of maternal smoking? And it matters, doesn't it? Now, that's an important issue for you. Now, there's one other point I wanted to make before we end this part of the session, and that is that gestational age for all of these models was not centered. Let's go back and look briefly at, for example, this particular model, where we modeled the log of the odds of low birth weight in terms of maternal smoking and gestational age. Now, what is worth noting here is that in this instance, this number makes sense to us. It is a difference. It is the assumed common difference between the two parallel lines. All right? That difference of 0.945. This number here makes sense to us. It is the slope. It is the slope that is assumed common to both the maternal smokers and the maternal non-smokers. So the slope and the vertical distance make sense to us, and these numbers are interpretable. Now this constant, though, let's take a brief look at this. That number of 15, anytime you see a logistic regression output and get numbers that are not in the usual range, right, where you can say this really represents a log odds, you have to ask, why is that? In this case, it is because of the fact that we did not center gestational age. And in fact, that constant refers to the non-centered analysis and refers to essentially a child of zero gestational age. In other words, it's where we have to draw the two lines back to the point where the gestational age is zero. So this is I would argue is a good case for redoing this analysis where you center gestational age at, say, the median or the mean gestational age for these children, or some number that's in the range of gestational ages. Okay? So it's worth keeping in mind that when you get a number that appears to be nonsense, you have to ask yourself, wait a minute, where is that? What is that about? And it's a number with no interpretation here, right? It is of no valid interpretation here. Now, in these models, the arithmetic and all of the calculations that are being done by Stata and or R with uncentered variables, they're using methods that are very numerically stable. And so we don't have to worry about the issue of the fact that that number of 15.5 is sort of a nonsense number. The other calculations are done well. And so what I will point out is that sometimes centering will matter, and that will come up in a much later session for a much later time. Okay, let's briefly look at the issue of centering and scale change. Let's suppose that we decided to repeat our analysis of the log of the odds of low birth weight using centered gestational age. And we'll center at 40 weeks, which turns out to be about the median in this instance. And if we do so, then we need to recompute then GC, which will be centered gestational age, and then the product SGC, that is maternal smoking times the product, times the centered or GC value G minus 40. And if we do that, we get very similar results to the uncentered analysis. Okay, let's have a look at the results here. What we can see is that the slope and the difference between the two slopes do not change. However, the intercept and the difference when the intercept is 0 does change. Okay? We can see that both B0 and B1 are specific to age equals 0 with the uncentered model, and B0 and B1 are specific to age 40 with the centered model. Now what we're getting, that number of 0.95, is very close to what we would want to use because of the fact that we're referring to an actual age, gestational age. Whereas in the earlier model, we got a number of 0.7 something, and that applies to no one. Okay. Similarly, the constant term or intercept here in this instance now refers to 40 or gestational age of 40. Okay. So that points out that that number minus 2 you can interpret, and I would encourage you to do that. The minus 2.056 is an actual value for a possible child. Okay? Now, what if we were to, instead of taking just a centered gestational age, but convert it from weeks to days. Again, what happens is we get the very same analysis as we got with the analysis of gestational age as weeks, except that now there's scale changes. And I would encourage you to have a look at the implications here. And now, in this instance, the two slopes change because they both refer to a slope and a difference between slopes, but now it's a rate of change per day, not per week. On the other hand, the numbers that are the constants in this instance, that is the vertical distance between the two lines and the value of the line for one of the two groups at age 40 does not change. So what we can see is that with location and scale changes, we do need to pay attention to the units. We can have that some characteristics change and some do not, and we can have other complicated circumstances. Well, now I'd like to take a few minutes and show you a bit of the graphics that Stata has that enables us to do many of the things that we'd like to be able to do in preparing presentation quality graphics. What I showed you in the earlier part of session 5 is fairly generic displays. The two-way display here without any options. So it doesn't have a legend and it uses generic names for the axes and there's no title. However, Stata is very nicely set up where you can have a legend, you can provide labels for the axes that are perhaps more appropriate, and we can have a title. Here the title I can construct using Greek letters and subscripts. This rather intimidating looking language is called SMCL. That's a part of Stata, SMCL. It's not that hard to use. Again, you just save the things and the features that you like in your scripts. Maybe not at quite as friendly as some systems. No matter. Let's then have a look at what the opening part of an analysis might look like if we had started our analysis using this do file. Let's have a look. And you can see we get this nice graph. Let's have a look at it. You can see we get the two lines, the red line and the blue line, but now labeled. So you can see there's the line for the non-smokers, and there's the line for the smokers. And we've got then the more friendly namings, gestational age here, fitted values, and then we have a title which uses Greek letters and subscripts. And that is a fairly attractive looking visual, and certainly more than adequate as presentation quality. And you can see how the results of that script end up when you run the do file. You see all of the commands that you've run, and indeed you can see the full display of the two-way command with the additional options. And you can see the other parts to this display that I've been doing for you.